Hello and welcome, my name is Mark. I'm a member of the Mathematical AI and Scientific Computing Lab here at Jung University, and today I want to talk about the paper Autoformalization in the Wild, Assessing LLMs on Real-World Mathematical Definitions, authored by Lanjiang, Marco Valentino, and André Freitasch. So, as the title of this paper already suggests, it is about using large language models for the task of autoformalization, which I'll define in a minute, and then to evaluate how well LLMs can do on this task. So let me guide you through the contents of this presentation. So first of all, I want to define what is autoformalization actually, and for that we need to know a little bit about formal languages. And then I'm going to talk about new benchmark data sets the authors created, so namely DevWiki and DevArchive. And then I'm going to talk about the experiments the authors conducted on these new data sets. First using zero-shot prompting only, and then some refinement strategies to enhance performance. And lastly, I want to talk about some limitations the authors mentioned in their paper. So let's begin. So what is autoformalization? So let S be a set of natural language statements enriched with some LaTeX symbols. So an element of S can be thought of a mathematical statement or a mathematical definition written in LaTeX code. And F is a statement in a formal language or a formal code. And the task of autoformalization basically comprises to, given a natural language statement, a natural language mathematical statement in the set S, we want to find its corresponding formalized statement in some formal language. If we want to do autoformalization using large language models, we can refine this function f in a way that not only takes a prompt p-auto for the autoformalization, but we can also attach some examples of mathematical statements and their corresponding formal counterparts. And we can add them to the prompt and ask the large language model to do formalization for us. So as an example, consider the statement where we want to prove that there is no function f from the set of non-negative integers to itself, such that f of n equals n plus 1987 for every n. So we are given this mathematical statement or this theorem in English, and we want to translate it to a formal code in the formal language called Isabelle, which will be used throughout this paper. So yeah, here you can see the correct solution. And so in the ideal case, what our LLM can do is we give it some mathematical statement written in LaTeX code like this, and it will output the correct formalized version of that statement. Okay, why should we care about this? So far, formalization, or more general, the automation of logic has one serious drawback, namely that it requires a lot of human effort to actually come up with formalizations of mathematical statements or mathematical theories. So if we can use LLMs to perform this task, then we can vastly accelerate the research in this topic of formal mathematics. And in this way, we can serve like a dual purpose. So not only are we going to accelerate formal reasoning tools, but we can also ground machine learning systems in verifiable and machine-checked knowledge. And so far, significant milestones could have been reached using formal theorem provers or formal languages. For example, after some long effort, the four-color theorem could have been proved or formalized using a formal language. And as you might know, the four-color theorem basically states that given a map, we can color it using no more than 4 colors in a way such that two adjacent regions do not have the same color. And other examples are the Kepler conjecture and the odd-order theorem. And examples for automated theorem provers or formal languages are Isabelle, as I just mentioned, and which will be used throughout this paper. And other examples are Coq, HOL Lite, Lean, Acta, and many more. And yeah, as I already indicated, if we can translate mathematical statements or mathematical theories into a formal language, then we can use automated theorem provers to check these proofs in a machine verified way. And this way we can be almost absolutely sure about the correctness of a proof, something a humanly written proof cannot provide. So here's another example. So we all know the theorem of Pythagoras. So a squared plus b squared equals c squared. And yeah, given that, we want to show that c squared minus b squared equals a squared. So we just subtracted b squared on both sides. And obviously, the statement is true. And indeed, Isabelle can show that this is true. And what if you try to prove something wrong? So in this case, I just removed the square from the a. So we assume that a squared plus b squared equals c squared. And now we want to show that this implies that c squared minus b squared equals a. And yeah, this statement is wrong. And the Isabelle theorem prover immediately finds a counterexample. So we can set a2 minus 1, b2 0, and c2 minus 1. And then this statement is false because minus 1 squared does not equal minus 1. And yeah, as you can see, Isabelle can automatically check if that statement or that theorem that we specified here in this kind of formal code is correct or not. So yeah, now that we know what is autoformalization or why we should care about like formalizing mathematical statements, we want to now evaluate how well can we use large language models to generate formalizations of mathematical statements, and therefore we need some benchmark data sets to assess this performance. So first of all, like there used to be, before this paper was written, there used to be benchmarks for exactly this task. So one of the most popular ones was mini F2F. And yeah, if we look at the examples of mathematical problems that are contained within this data set, so like number 1 here, number 2, what's the sum of two values of x for which x plus 3 squared equals 121. As you can see, these examples are like high school level. So if you're a smart high school student, then you are able to solve these problems. However, what we want to do is we want to formalize mathematical statements that naturally occur, like in a research-based setting or in university. So existing data sets, they only contain like elementary objects like integers or fractions and some basic operations. But what we want to do is we want to handle mathematical statements that contain more abstract concepts like vectors, matrices, topologies, probabilities, calculus, and so on and so on. And yeah, so far before this paper was written, there haven't really been data sets or benchmarks to evaluate large language models for the task of autoformalization of some like higher level mathematical statements. And this is why the authors came up with two new ones, namely DevWiki and DevArchive. So they want to collect mathematical definitions of two types, common definitions and specialized definitions. So the common definitions are definitions that are embedded in some kind of global context, that have some implicit and more general preliminaries. And we've got specialized definitions that are based on some local context where the preliminaries are explicitly given and in some cases very specific. And yeah, a good model can handle both kinds of definitions. So in order to get some common definitions and to make a data set out of them, the author suggests to use mathematical statements from Wikipedia, and for specialized definitions, the author suggests to use archive papers. And in both cases, we're using mathematical definitions that stem from the field of machine learning. So let us look at some examples of definitions that are contained in these two data sets. For example, for DevWiki, we've got the definition of Rademacher complexity, which is some measure of how well can elements of a set correlate with some random noise, which is distributed according to the Rademacher distribution. Or a second one would be the definition of a polynomial kernel, which we all might know from basic graduate level machine learning classes. And some definitions that are contained in the dataset dev archive is, for example, the definition of a covering number, which is based on the more advanced concept of a metric space, or the definition of a trimmed mean, which is a generalization of the mean functions specifically suited for random variables xi that have a heavy tail. And yeah, in the computation of the mean, we want to account for the fact that xi is heavy tail. So yeah, to give you an idea how these datasets look like, I gave you these examples. Let's compare them. So our main motivation was to construct datasets that are more complex and more advanced than, for example, the existing benchmark datasets like MiniF2F. And we can see that DevWiki and DevArchive both contain, on average, more tokens, more mathematical objects, and more formulas. On average, and also in parentheses, you can see the standard deviations for these values, and in all cases, they are higher than for MiniF2F, which indicates that the datasets DevWiki and DevArchive have a higher diversity or a higher variation within. So yeah, thereby the authors claim that the new datasets DevWiki and DevArchive are particularly suited to evaluate large language models for the task of autoformalization. Okay, so now that we've got some new datasets to evaluate large language models on the task of formalizing complex and higher level mathematical statements, we want to do some experiments and check basically how well do LLMs perform for this task. So which LLMs are we going to consider? So in this paper 3, we're considered DeepSeek Math, which is an LLM of smaller size. It only has 7 million parameters, which was specifically trained for solving tasks related to mathematics. And also the authors considered Llama and GPT-4o, which at the time of the publication was widely regarded as one of the current state-of-the-art large language models across many tasks and many domains. And how do we want to measure performance? So one obvious metric will be the pass rate. So we're just going to check if the formal code generated by the large language models passes the type checker. And the second metric is the first error offset, which is the fraction of correct lines before the first error occurred in the formal code that was generated by the large language model. And in the ideal case, it's going to be 1.0 for a formal code which is totally correct. And besides these two general metrics, the authors also break down like which types of errors occurred how often. So for example, syntax errors, errors that stem from undefined objects or references, or TOF errors, which are basically type errors. So in this table, we can see the results for zero-shot prompting and for zero-shot prompting using binary refinement. So in this case, like the authors just gave the prompt of like, please formalize the statement. And in this case, ZS plus binary, they gave the prompt to auto-formalize the statements, and also gave the LLM some previously generated examples with a binary label whether that formalization was correct or not. And if we look at this table, so what we can see is that indeed the datasets DevWiki and DevArchive are harder than the mini F2F set. So as you can see, for the mini F2F dataset, which contained of these like more simple high school level problems, the pass rate of GPT-4 was 25%, but for DevWiki it was only 10%, and for DevArchive 13% if we only do zero-shotting. And also you can see like the fractions of like the correct lines before the first error is much higher in this case for GPT in the mini F2F case than for DevWiki and DevArchive. What we can also see is that a specialized smaller model like DeepSeek Math can reach a similar performance as the state-of-the-art model GPT. So for example, for just zero-shot prompting, the pass rate for DevWiki and GPT was exactly the same, namely 10.87%, and also the same for DevArchive, 13.33%. And another thing that we can observe here is that if we do not only do zero-shot prompting, but also we give the LLM some example codes with their binary label of correctness, then we can see that if we do that, in many cases for the smaller models, performance actually goes down. So you can see here, actually in all cases, the pass rate for DeepSeek Math actually goes down if we provide some more examples. So here it's degraded from 3 to 2%, 10 to 6%, or 13 to 3%. Whereas for GPT, if we do that, the performance is enhanced. So if we give some examples into the prompt, then in all cases, the performance increases. So this indicates that only like the large language models with like many billions of parameters have this capability of self-refinement, whereas the smaller language models like DeepSeek Math or Llama do not. So what can we do to improve these results? So first of all, let's analyze in more detail the errors. So this analysis is based on the outputs that GPT-4 has given. So for example, for syntactic errors, what we can see is that GPT misses, for example, if you want to use an implication arrow, like right arrow in Isabelle, it has like these extra left angle, right angle symbols, which GPT often like forgets at the end. Or GPT would assume that in Isabelle there's a symbol called mathcal, which does not exist actually in Isabelle. And if we use that, the code will be wrong. And also like sometimes the formal codes generated by GPT-4 have some kind of name conflicts. For example, it uses the keyword instance, which is already reserved by Isabelle and cannot be used for new items. And also, in many cases, GPT uses some objects or items that have not been previously defined, or GPT produces mismatches in types for functions. For example, in the previous example, we saw that we're defining functions from natural numbers to natural numbers, and suddenly like this function would take a real number or a complex number as an input. And this is going to yield a type unification error, TUF. And based on these errors, the authors propose some refinement strategies. So first one is categorical refinement. So this is what we already did before. So we only give like the previously generated codes with some kind of label if they were correct or incorrect. And also we can give some like detailed feedback. So we add previously generated codes to the prompt. And if they were wrong, like we provide like what was the type of the error message, and like the exact location of that error. And also for each major error category, like syntactic errors, undefined errors, and type unification errors, the authors designed some like specifically targeted correction instructions for these errors. Let's look at the prompts that the authors used. So yeah, if we just do the plain version, we're just adding some previously generated codes. And yeah, we're telling the LLM you can choose to refine this piece of code for your task. And in the binary case, we attach some previously generated codes and also provide information whether these codes were correct or not. And for detailed refinement, what we do is we attach some previously generated codes and also tell the LLM if they were wrong, like why they were wrong. So the error details and where the error code is located in the code are, and you should refine this piece of code for your task. And also like we designed some like specific prompts to to try to make sure that the errors that previously occurred do not happen again. So like we specifically asked the LLM to like add this like extra symbol at the end of like, for example, write error. And also we specifically ask the LLM to make sure that every item that is mentioned in the code also has a clear reference, and also similar thing for type unification errors. So these are the prompts that the authors used to try to enhance the performance. Okay, so let's have a look at the results. So here in red, we can see that if we provide the large language model details about its errors, either just binary or with like detailed error explanations, then we can see that we can improve the performance in all cases. And also for the specific error categories, we can see that performance can be enhanced by giving more details about the errors that the large language model makes for autoformalization. And another thing that we can observe is that if we refine our prompts based on the specific error categories, then this will also enhance the performance of autoformalization in many cases. So we can see that for syntactic errors, the best performance actually was reached if we use a combination of detailed error feedback combined with categorical refinement for syntactic errors for both the DevWiki and DevArchive dataset here in dark green. And also for undefined errors, this approach of combining detailed error feedback together with categorical refinement is very effective, as we can see in dark blue. So for mini F2F, the error rate is very small, and it's the smallest for both DevWiki and DevArchive. However, another thing that we can observe is that if we only use the categorical refinement prompts without detailed error feedback, then yeah, in many cases, the performance doesn't get much better. So for example, here in light green, we can see the syntactic error rate for the DevWiki dataset using only that kind of categorical refinement for syntactic errors, and we can see that the performance is just improved very little. And for example, here for UDF errors, we can see that the performance actually gets worse. So let's wrap that up. So we saw that providing LLMs with more information about individual errors is more effective than simply indicating binary correctness in many cases. And categorical refinement tailored for specific error categories can effectively reduce errors for that specific category. However, if we look at the type unification errors, we can see that those ones are more hard to correct. For example, in particular for the dev archive dataset, we can see that performance actually gets worse if we use detailed feedback together with TUF tailored categorical refinement. So here in dark purple, the error rate was one of the highest actually, even though this prompt is specifically designed to lower TUF errors. So the authors introduced two more refinement categories. First one is symbolic refinement, specifically for syntactic errors. So this is, for example, in this case where we saw that this closing symbol is missing, then we just add it to our LaTeX code. So instead of using just like slash right arrow or long right arrow, we like using this kind of symbol that Isabel would use. And yeah, in the same way we can do that for like this issue with mathcal symbols. So instead of using like mathcal, we're just replacing them with their valid Isabel counterparts. And another refinement approach that the authors are suggesting is formal definition gathering. So what they do is we just provide all the relevant formal definitions for the objects that appear in our formal code. We just provide it like additionally to the formal codes that are generated by the LLM. So how do they do that? They first collect external formal definitions of mathematical items and their sources from the Isabel HOA library, and then they filter like all those definitions that might be useful for the autoformalization tasks based on our data sets, and then they will like manually select them for each instance. Okay, so let's look at the results of using symbolic refinement and formal definition grounding. So yeah, we can see that in almost all cases, we can reduce the overall error rate for all data sets. And so one thing that we can observe is that if we only use symbolic refinement, we can reduce, of course, syntactic errors. However, in many cases, performance with respect to undefined errors or here type unification errors might drop. And another thing that we can see is using FTG, or in this case post FTG, where we just replace the preambles after they were generated with the formal definitions that we've gathered. And we can see that in particular for undefined errors, this kind of approach can be very effective. And however, one limitation that we can already see is that in many cases, even though we're using symbolic refinement and FTG together with detailed error details, then we still have a hard time to reduce the type unification errors. And yeah, this is summarized on this slide. So symbolic refinement can effectively reduce syntactic errors in generated formal codes and definition data sets. Replacing preambles with post FTG leads to overall higher syntactic correctness, and FTG is particularly effective for reducing undefined error rates. However, one thing that we can observe is that the errors are somewhat entangled. Like Unlike many F2F, auto-formalized codes for definition datasets tend to contain multiple intertwined error types within a single code block. So as a result, if we reduce one error category, so we've seen that, for example, for syntactic errors, if we reduce the error rate in this case, we can increase the error rate in another one. Or here, for if we use FDG, we are gaining performance with respect to UDF, but our performance is decreased with respect to syntactic errors or type unification errors. So that brings us to the limitations that the authors mentioned in their article. So first of all, one limitation is that their error analysis was like very specifically targeted for the formal language Isabelle, and some of the results that we've observed may not generalize well to other formal languages. Second one is that the proposed benchmark data sets are relatively small, so they just contain, in both cases, less than 100 examples. So future work might address to expand these data sets. And as we have seen just now, is that the proposed refinement strategies can reduce the error rates. However, they do not fully eliminate them. And for example, in the case of type unification errors, like it still remains somewhat open how we can resolve those. And with that, I would like to thank you for your attention to this matter and for everybody who has listened to this video. Thank you.